yesterday or a couple days ago, whenever it was, and we're going to talk about the three situations in which limits do not exist. And the three situations where limits do not exist are, number one, where the behaviors differ from the left and the right. So if you're heading in from the left, you're approaching one value, and when you're heading in from the right, you're approaching another value. An example of that is the limit as x approaches 0 of the absolute value of x divided by x. Not that I expect that you know what that graph looks like, but I do have a sketch of it right here. And as you are coming in from the left, the graph is approaching a y value of -1. But when you are coming in from the right, it's approaching a y value of 1. Therefore, the limit does not exist. And you can, I don't have this in my notes, but you can just say that that limit is equal to DNE, which stands for does not exist. All right. The second situation when a limit does not exist is if you have unbounded behavior. When I say unbounded behavior, I mean the graph is heading one direction infinitely far. Then the limit does not exist. So, for example, the limit as x approaches 0 of 1 divided by x. This is the x value of 0. And as I'm heading in from the left, the graph is heading infinitely far low. That means it is unbounded. That means it doesn't end. It keeps going and going and going. And it just so happens in this case that not only is it heading infinitely far low, but when you come in from the right, it is going infinitely far up. So they're not even approaching the same direction. These two happen to be approaching completely different directions. There might be a time, though, when the graph is heading down like this on the other side. That is still considered unbounded behavior, even though they are both heading infinitely far low. Are you okay with that?
Yes.
So that is another situation when the limit does not exist. Oscillating behavior, we kind of talked about that a little bit earlier today. Oscillating behavior. Oscillating just means it's like zigzagging. It's going up and down and up and down and up and down really, really fast. Like so fast that you can't even control what's happening. And by the way, my graph that I have up here, I did not do justice for the graph. It looks a lot better if you look at pictures or graphs in your textbook. But an example of that would be the limit as x approaches 0 of the sine of 1 over x. So if you were to look at a table of values for this situation, your table is going to oscillate, meaning it's going to go from a positive to a negative to a positive to a negative to a positive to a negative. It's going back and forth and back and forth and back and forth. In other words, it is so crazy that you cannot determine what the limit is because you don't know which end is up. So another situation when the limit is DNE, does not exist. All right, I'm going to sum this up. 3 things I need to say, and then we're done talking for the hour. Limits can be estimated using one, or all of a 3-pronged approach. So in other words, if I ask you to calculate a limit, you have 3 choices. Sometimes one way is the best way. Sometimes another way is the best way. Sometimes you might have to use all 3 to get an accurate answer. All right, and those 3 approaches are, the first being, do you guys see me just try to erase that? The first being a numerical approach. A numerical approach means you create a table. And remember, when you create a table and set up your table counter, in other words, the change in your table, to be equal to, it seems to work nicely, if you are counting by 0.001s. If that doesn't work, try something else. Try 0.00001. see what happens. You could also do it graphically. That means draw a graph, either do it by hand or look on your calculator. And then the third approach is to do it analytically, which means you're just using algebra or calculus when you have a little bit better handle on what calculus is. So I'm going to give you one more example because a lot of the problems that you guys have to do today are going to require you to do what I'm going to show you right now. Let's say an example. And this would be an example that would go along with number 3, the third approach, using algebra to calculate a limit. Let's say that I ask you to calculate the limit as x approaches, I don't know, we'll say 3, of this function, 2x squared minus 4. 2x squared minus 4. You certainly could go to y equals, you could type in 2x squared minus 4, you could make a graph, you could make a table, and you could figure out what the limit is supposed to be. But when you have a nice, easy algebraic equation like this, all you really have to do is take this value of 3 and plug it into your rule. So you plug it right in
Well, I
here.
think we did this last year.
Yeah, you probably did. So really, all you have to do is calculate the value of the function by doing 2 times 3 squared minus 4.
You get 14.
You get 14 things. So the values, the limit as x approaches 3 of 2x squared minus 4 would be equal to 14. So some of these today are going to be pretty simple. You'll enjoy them. Enjoy it.